This last section of the book is entitled Applications of Differential Equations. In fact, we've looked at applications of differential equations even more or less throughout the book, but certainly in the last couple of sections. So in this section, I just want to hit some more interesting separable differential equations and in the midst of word problems. So there won't be any new theory. It's just some word problems. So let's start with a population problem. So suppose you've got P equals P of T equals a population at time T. What do I mean? I mean that maybe we're looking at people, maybe we're looking at animals, maybe we're looking at bacteria, a population of something measured in some time units. Like if it were people in a city, you might want to use years. If it's bacteria in a dish, you might want to use hours. In some time units. Populations typically change for, well, I'll think about a population of people, but the same kind of thing that I'm about to say would apply to animals or to bacteria. Why do populations of, say, cities change? Well, there are new people being born, there are people dying, and there are people moving in and out of the city. So those are the typical reasons why the population would change. And so the rate of change of the population with respect to time, dp dt, well, there are four rates involved here. There's the rate at which people are born, per whatever the time unit is, minus the rate at which people die. I'm now assuming we've got a population of people, so not bacteria, not some other animals, right, at which people die. Then you would add the rate at which people move in. And you would subtract the rate at which people move out. If you think that, well, that wouldn't apply to bacteria in a dish, they don't move in and out, well, you could remove some bacteria or introduce new bacteria. So yes, the same sort of thing does apply. Even in that case, part of what makes these differential equations interesting is the way we typically specify birth rates and death rates. They're not, they're usually specified by saying the birth rate is 3% per year. Well, they don't mean 3/100ths of a person per year are born. They mean 3% of the current value of P. And the death rate is the same thing. If they say like 1% of the population dies each year, that's 1% of the population. So it's given to you as a fraction of P. So what we usually write is that dp dt equals this is a beta for the birth rate times P. So this is called the birth rate as a fraction of P, the birth rate I'm going to pick years now just to fix a time unit. Birth rate per year as a fraction of the population. This is how we normally talk. So if you say 3% of the population, or the birth rate is 3%, then beta would be 0.03. And then it gets multiplied by P to give you the actual people per year, birth rate that are born. Birth rate per year as a fraction of P. Similarly, we have minus delta P, and that's a lowercase delta, delta for death rate, as a fraction of the population. Per year, as a fraction. Of P. And then the rate at which people move in and move out, it varies how people describe that. Sometimes they give absolute numbers like 5,000 people move out each year and 1,000 move in. Occasionally you'd hear that given as a fraction of the population, so a certain percentage of the population moves in and out. But in our example, we're going to actually just have fixed numbers. So there's some plus the net change due to moving. You might as well lump them together. The net rate of change due to moving. So people moving in and moving out. So let me pick some numbers and let's look at what happens. So suppose we start with a city with a population of 500,000 people. So suppose at 1, January 1st of 2009, or 2009, the population is 500,000. We're going to call January 1st of 2009 times 0. So this is t equals 0 years. So t is the number of years since January 1st, 2009. Suppose the population is 500,000, okay? And that the birth rate, suppose the birth rate is 3% of the current population, and the death rate is 4%. And the death rate, the annual, let's say the annual birth rate is 3%, and the annual death rate is 4%. And then let's say the net change, so the annual change in population due to moving is 1,000. So they gain 1,000 people per year from people moving in. Okay. What would we like to know? Find the population as a function of time. Okay. Well, we get a differential equation with an initial condition. So we get an initial value problem that we'd like to solve. So you get dp dt equals the birth rate, 3%, so 3/100 of p, minus the death rate times p, so minus the death rate. And then we gain 1,000 people a year. So this is an equation about rates of change. This is the rate of change in the number of people per year. And then this is the people per year who died, who were born. people per year who died, and then people per year that have moved into the, well, net people who have moved into the city. Maybe 4,000 left and 3,000 came in. Okay. Our initial condition, P at 0, is 500,000. Okay, we'd like to solve this differential equation. This is dp dt equals negative 0.01p plus 1,000. This is separable. You divide by this whole function of p and multiply by dt. It'll be slightly nicer. It's slightly easier. We don't have to do what I'm about to do, but things will work out slightly more nicely. If you factor out the negative 0.01 and write p minus, and then you'd have to divide this by negative 0.01. Well, that's dividing by 100th, negative 100th. So you multiply by negative 100, and so we get minus 100,000. All right. And we'd like to solve this and then put in the initial data. Well, there's one equilibrium solution that we should worry about. Of course, it doesn't satisfy the initial data, but one equilibrium solution is, this is an equilibrium solution. So it does not satisfy the initial data, so it is not a solution to our initial value problem. I do want to say something about this later, but all right, not a solution to the initial value problem. Okay. So then, all right, but we've recorded that. Now I'll divide both sides by p minus 100,000, multiply by dt, integrate both sides, and see what we get. Okay, so you divide both sides by p minus 100,000 and multiply by dt. You get 1 over p minus 100,000 times dp equals negative 0.01 times dt. You get this, and you integrate both sides. All right. Over here, there's no question what you get. You can pull this constant out, an antiderivative of 1 with respect to t. It's just t. And I'll put a plus c over here. How do you integrate 1 over p minus 100,000? Well, if it were just 1 over p dp, you'd get the natural log of the absolute value of p. It's not just a p, but it is just p plus or minus a constant. So the substitution, if you let u be p minus 100,000, then du, the differential of this, is just the derivative of this times dp, but that's just 1 times dp, so du is dp. And this integral immediately becomes the integral of 1 over u du. Right? Dp is du, this is now 1 over u. So we get the natural log of the absolute value of u. I won't put a plus c here because it's on the other side. And you put back in that u is p minus 100,000, and you quickly get this. Great. That's what we get. We'd like to solve for p. So what do? Well, you do what we did in the last section. You raise e to both sides. So you get e to the natural log of the absolute value. You want to get rid of the natural log and raising e to powers. So applying the exponential function is the inverse of natural log. So do this. And as we did in the last section, raising e to the power is taking natural log inverse function. So you get the absolute value of p minus 100,000 equals, you factor off in e to the c times e to the minus 0.01t. Right? When you multiply two things with the same base, the exponents add, so this equals that. We don't like the absolute value signs. We can eliminate those, but we have to insert a plus or minus sign over here. But e to the c is a constant, plus, which has to be positive, but it's a constant. Plus or minus that then is a positive or negative constant. I'll just call it b. We get this equals b e to the minus 0.01t. And so our general solution, including this equilibrium solution, we get p equals 100,000 plus b e to the negative 0.1t. Okay. In fact, this solution includes that one. If you just let b, our method of derivation told us that b had to be positive or negative, not 0. But by letting b be 0, we get this other solution. So this is what every solution looks like, where we can let b be any real number. Now you plug in the initial data, that when t is 0, p is 500,000, and you get 500,000 should equal 100,000. Plus what you get when you plug in t is 0, this would be 1, e to the 0 is 1. So b is 400,000. In our solution to the initial value problem, then you combine this with this, we get that the population is 100,000 plus 400,000. That's not going to fit there. Plus 400,000 times e to the negative 0.01t. So this is our solution to the initial value problem. Notice that as time goes on, if you just let time keep going, then that's like letting t go to positive infinity. Then this exponent goes to negative infinity. So that's e to the negative infinity. That's 1 over e to the infinity. 1 over something really, really, that's arbitrarily big. Yeah, this approaches 0. So as time goes on, your population approaches 100,000, the equilibrium solution. Yeah, so your population keeps decreasing as time goes on. It starts at 500,000, it keeps decreasing, and it approaches 100,000. Theoretically, it would never reach 100,000, but we made a lot of assumptions about the existence of fractional people here, and that birth rates and death rates are continuous when that's only an approximation. All right, let's look at a completely different kind of problem. Let's look at an object moving through some fluid. So here's another example. Suppose I have an object moving through some fluid. So I don't know, imagine a tank full of oil or air or whatever. You've got some object of mass m. So the mass is m. I don't care in what units, just make them consistent. The mass is m. And it's moving through there, and we're going to assume that the only force acting on the object is the force of fluid resistance. So when the object is moving that way through like a tank of oil, the oil pushes back at it, so that fluid resistance acts on it. You might go, well, gravity certainly acts on it. We'll either imagine we're doing this in space, or we only care about the force that's opposing the motion that way, so we don't care about the motion, the forces acting downward like gravity. In any case, we'll assume there's only one force. The force acting, the only force acting on the object is the force of resistance from the fluid, the force of fluid resistance. And it is typical to assume that fluid resistance is proportional to some power of the velocity. So for a lot of things, the fluid resistance is proportional to the velocity. For other types of problems, fluid resistance is more closely proportional to the velocity squared. And you could take different powers of the velocity. In different situations, you might get different powers of the velocity. These things are determined experimentally. I'm going to say, in this problem, just to give us an interesting problem, the only force acting on the object is the force of fluid resistance, and I'm going to say which is proportional to the velocity squared. Okay. And it always acts in the direction to oppose the motion. So I'm going to assume that there was some initial velocity and that we chose our positive direction so that that initial velocity is positive. I'm just saying our positive direction we choose to be the direction in which the object is initially moving. Great. So what do we get from this? Well, we use Newton's second law of motion. Which says that the sum of the forces acting on an object, and we're assuming that's only the force of resistance, equals the rate of change of the momentum, but we're assuming the mass is not changing. So it's just the mass times the acceleration. So we will get that the mass times the acceleration, but the acceleration is the derivative of the velocity. So the mass times the acceleration is the sum of the forces, but there's only one force. And that's the force of resistance, which is proportional to v squared. That means it equals a constant times v squared. And I'll make the constant positive so that negative, this is a negative force, which indicates that the force is pushing in the direction in the negative direction, the direction opposite the velocity. Okay, so we get this differential equation. And the question is what? Find, command, the imperative, find the velocity as a function of time and the position as a function of time. Well, this is a separable equation. And we're assuming that our initial velocity is not zero. So I'm not going to bother looking at the equilibrium solution this time. I'm just going to assume that the velocity is not zero and see what I get. Right, what happens, maybe I should say, what happens if your initial velocity is zero? Then there's an equilibrium solution that is your velocity is always zero. Well, really, no kidding. This says that if the only force acting on you is proportional to the velocity squared, and you start out not moving, well, then there's no force on you, and you're never going to move. So your velocity will stay zero, and your position will stay at whatever it was. So if v naught is zero, this problem is very silly. Nothing happens. The object just stays where it was. So, all right, but we're assuming v naught is not 0. So we don't worry about v being 0 in this. We'll divide both sides by v squared. Divide by m, multiply by dt. We get v to the minus 2 dv equals minus k over m times dt. And then you integrate both sides. This is the power rule. You add 1 to the exponent, divide by the new exponent. This is just a constant. You get the minus the constant times t plus an arbitrary constant. So you get this. We would like to solve for v, the velocity, so you multiply both sides by minus 1. You get v to the minus 1 equals k mt minus c, but c has no meaning for us, so minus c plus c, we'll just call it c again. You get this. And I'm going to plug in my initial data now. Now is a good time. We could go ahead and finish solving for v, then plug in the initial data and figure out what that means c is. But then we'd have to undo some of the algebra that we need to do in a minute. I mean, if we solve for v first, then c will be in the equation in a more complicated way that we'll have to undo to figure out what c is. So now is the best time. We plug in that when t is 0, v is v naught. So we plug in the tautological initial data. When t equals 0, v equals v naught. All this says is at time 0, the velocity equals the velocity at time 0. And so we get v naught to the minus 1. Remember, v naught is not 0. Equals, if t is 0, this is 0 plus c. So that c is v naught. So c equals v naught to the minus 1. Sorry, v naught to the minus 1. And so, this is very important. I almost put this c in here. We need to put it in here. What we meant by c changed from this line to this line because I multiplied by minus 1. And I called minus c, c again. That's fine. I mean, we could have called it minus c, solve for that c. We'd get the same thing either way. But what you can't do is absorb the minus 1 and call this c again, then solve for this c and then plug it back in there like I was about to do. That would have been very bad. This goes in there. So you get, the last time we determined that c. So we get v to the minus 1 equals km over t plus v naught to the minus 1. And then you take reciprocals. So v is 1 over this, and I'll write v naught is 1 over that. So what we get is that v is 1 over k over m times t plus 1 over v naught. For aesthetic beauty, I know I'll do this. Multiply the big numerator and denominator by v naught, and we get v naught over v naught times k over m, so v naught k over m times t plus 1. And that's what we get for v. This has the advantage of, if you started at v naught equals 0, it would give you the equilibrium solution so that we don't have to worry if we write our answer like this about whether v naught was greater than 0 or not. Okay, so that's v. How do we find the position? Well, the velocity is the derivative of the position. So this equation is dp dt equals v naught over v naught k over m times t plus 1. And so this equation for the velocity is the same as saying the derivative of the position with respect to time equals this. So p is an antiderivative of this. So we solve this, which just means you anti-differentiate. So p is it's the general antiderivative, is an antiderivative of v naught k over m t plus 1 times dt. How do you integrate this? Well, you make a substitution. V naught's a constant, we can pull that out. This isn't just 1 over t dt. If it were, we'd get natural log of the absolute value of t. But it's just a constant times t plus a constant, and so it's almost like it's just a t. So make the substitution. We'll let u be v naught k m t plus 1. Then du is the derivative of this with respect to t. Well, that part gives you a 0. Here you just get the constant. So you get the derivative of that with respect to t times dt. So du is this. Or taking this and putting the v naught k m divided by m on the other side, we get dt equals m over v naught k times du. And so this integral becomes, all right, what do we get? Well, I'll leave the v naught up there for a minute. You get v naught stays in the numerator. This is just u. dt now is m divided by v naught k times du. Well, this v naught cancels with this v naught. The m over k is a constant, so you get m over k times the integral of 1 over u du. But that's the natural log of the absolute value of u. So we get m over k times the natural log of the absolute value of u plus a constant. And then you put back in what u is. So what are we getting? We're getting that p is m over k times the natural log of u. So times the natural log of the absolute value of v naught k t over m plus 1 plus c. We don't actually need the absolute value signs. We're only doing this for positive times. V naught's positive, k is positive, m is positive. So we're taking absolute values of a positive number, so we don't need the absolute value signs. They're not wrong. We'd like to give some physical meaning to this c. How do you do that? You put in the tautological initial data that the position is the initial position when t is 0. When t is 0, you get the natural log of 1. The natural log of 1 is 0. So p naught is c. So our solution for the position is this. That the position equals m over k times the natural log of v naught kt over m plus 1 plus the initial position. Okay, so we've seen an application to population models. We've seen an application to objects moving through a fluid. Let's do an application to crime. What? Let's look at another example. So, if you've watched any of these crime shows that are on, you probably know that they frequently measure the temperature of the liver to determine how long a corpse has been dead. Why do they do that? Well, they do that because the liver is maintained at body temperature, so we'll approximate that as 98.6 degrees Fahrenheit. The liver is maintained at body temperature while you're alive. Once you die, your body stops regulating its temperature and your temperature starts dropping, assuming the outside air is colder than 98.6. So, if they know the temperature of the outside air, so that's usually referred to as the ambient temperature, and assume that it's been constant, or if it hasn't, it's a more complicated problem, we're going to assume it's been constant. So maybe they found a corpse in an air-conditioned room. So if you know the outside temperature has been held constant, and you measure the liver temperature, they actually have a constant. They know the approximate values of how fast livers lose their heat or how fast the temperature of the liver changes, then you can tell how long the corpse has been dead. And what's really going on here is Newton's law of cooling. It's also Newton's law of heating, but in this problem it has to do with cooling, and it's what theorems call. Newton's law of cooling says and it doesn't matter what temperature scale you're using, it would change the proportionality constant I'm going to refer to, but if T, capital T, equals the temperature of an object at time t, placed in surroundings with a constant temperature T sub amb, that's short for the ambient temperature, so then the rate of change of the temperature of the object with respect to time is proportional to the difference between the ambient temperature and the temperature of the object. Physically, this should seem very reasonable. What it says is if you put something, say, very hot in a very cold room, so that the temperature difference is great, then the object starts cooling off very rapidly. On the other hand, if the temperature of the object is very close to the temperature of the surroundings, then the object doesn't cool that rapidly, so the rate of change of its temperature isn't that great. So that's what Newton's law of cooling says, and as a differential equation, what it gives us is the rate of change of the temperature of the object, dt dt, one of those is a capital T and one's a little t, is proportional to, so equals a constant times, the difference between the ambient temperature and the temperature of the object. So that's a constant, that's a constant. K, is it positive or negative if I write things like this? Well, I mean, physically, it'll work out regardless of how we write it. We can figure out whether it's positive or negative after we put in some numbers, but physically you should be able to do this now. We're going to put a warm object in cooler surroundings. So you would expect, you put a warm object in cooler surroundings, the object should cool off. So the rate of change of its temperature should be negative. Its temperature should drop. Okay, so we want, if this is big, and this is small, so this is negative, we want this to come out to be negative, so K needs to be positive. You might think, oh, well, it would be negative if we started with a cool object and put in hot surroundings. No, it would still be positive, because if you put a cool object in hot surroundings, the object should heat up, so dt dt should be positive. But if you put a cool object in hot surroundings, this is already positive. You want this to be, you know this should be positive, so K is still positive. So you get this from Newton's law of cooling. And so now let's suppose, so meanwhile, back at our corpse, so you find a corpse under normal conditions, and what that means, you'd have to ask a criminologist, but relatively normal conditions. So we're going to assume that our ambient temperature, we know that it's been 72 degrees Fahrenheit for a long time in the room. We're going to assume that we find the liver temperature at the time we find the corpse. The liver temperature is 80 degrees Fahrenheit. The K, the value of K, we're going to assume this is approximate, but it's 0.08. I think that's right. Yeah, 0.08 per hour. All right. So what do we get for so what's the question? We want to solve this for t as a function of t. No, that's not quite true, but suppose we solve for t as a function of t. Then what we'd like to do is plug in that the temperature is 80 degrees and figure out what it was at time 0. Right? We'll say t equals 0, so t equals 0 hours is when the person died. So we're trying to figure out how many hours have gone by if the liver temperature is 80 degrees Fahrenheit. So what do? Well, you plug in some numbers and you solve the differential equation. You put in that capital T is 80 degrees Fahrenheit, and you solve for little t, the number of hours. So we get dt dt equals k, which is 0.08, times the ambient temperature, 72 degrees Fahrenheit. I'll drop the units, they're all consistent. 72 minus t. We don't know t at, yes, and we do know t at time 0. T at time 0, the initial temperature of the liver is we're assuming it's 98.6 degrees Fahrenheit. What we'd like to do is solve for little t when big T equals 80 degrees Fahrenheit. So, all right, this is in degrees Fahrenheit per hour, degrees Fahrenheit per hour. Okay, so what do? Well, this is separable. You can divide both sides. In fact, I'll factor out a minus just because I can, but so let's write this as dt dt equals negative 0.08 times t minus 72. You don't have to do that. It's a minor convenience. Divide both sides by t minus 72 and multiply by dt. We get 1 over t minus 72 times d capital T equals minus 0.08 dt, d little t, and you integrate both sides. Just like we did before, you make the substitution u equals t minus 72, then du will be dt, and so you just get the integral of 1 over u du. That's the natural log of the absolute value of u, but you put back in that u is t minus 72. I'll let you do that yourselves, but you just make the substitution u equals t minus 72, and you find that you get the natural log of the absolute value of t minus 72 equals negative 0.08 t plus a constant. All right, so we're here. Okay. In other problems, what we've done at this point is solve for capital T. It helps to look ahead at the question, though, because in this problem, we're going to be given a capital T and ask for a little t. That means you'd like to have little t as a function of capital T, not the other way around, not capital T as a function of little t. So, in fact, I'm not going to raise e to both sides here to solve for capital T. I'm just going to leave it like this, plug in our initial data, and then plug in that capital T is 80 and figure out what little t has to be. So what do you get? So we've got the natural log of the absolute value of t minus 72 is negative 0.08 t plus c, okay, where t is in hours. Little t is in hours and capital T is in degrees Fahrenheit. We also know that t at 0 is 98.6. So you plug that in. You plug in that capital T is 98.6 when t is 0, and so you get that this is c. So c is, this is the natural log of 26.6. That's what c is. All right, so you plug that back in and you get the natural log, the absolute value of t minus 72 equals negative 0.08 t plus the natural log of 26.6. Now we want to plug in that capital T is 80 and solve for little t. So we want, when capital T is 80, this is the natural log of 8. We want the natural log of 8 equals negative 0.08 t plus the natural log of 26.6. We're trying to solve for t. Put this negative term over here, subtract this from both sides. You get that 0.08 t is the natural log of 26.6 minus the natural log of 8. And then divide both sides by the 0.08. You should certainly get out a calculator to do this. It's the difference of natural logs is the natural log of the quotient, so it's roughly the natural log of 26.6 over 8. That's approximately the natural log of 3, but then divide by 0.08. I suggest getting out a calculator. You should get that this is almost exactly 15 hours. And that would be our estimate of how long the corpse has been dead. Okay, well, that's another application. Let's do one last one, kind of businessy economics problem. So let's look at let's look at one last example. We're back at January 1st, 2009. And we've got a company. Company starts selling a new heavy wool coat. We're interested in W, which is WT, equals the number of wool coats they've sold after t months. So t equals 0. Well, they just started selling, so at t equals 0, they've sold none. T equals 0 would be January 1st. So we're assuming W at 0 is 0. Okay. Well, we need some more data. So we'll suppose that the company has done a market study, so that market research starts selling a new wool coat in a small city. So they're selling this in a small city, and they've done market research, and they've discovered that there are at most 1,000 possible buyers for their new wool coat. And that at a given point in time, the rate of change in the number of coats that they've sold is proportional to the number of these possible buyers who have not yet bought one. So that, if there are twice as many people who haven't bought one, then the rate at which people buy them is twice as great as it would be otherwise. So what this says is dW dt equals some constant. It's proportional to 1,000 minus W, except, this is null. I was saying at a fixed point in time, they've decided that the rate of change of the number of coats they've sold, so the rate at which their coat sales are changing, is proportional to the number of people who have not yet bought a coat. So that's 1,000 minus the number who have bought a coat. But, in fact, there are seasons, and you sell a different number of wool coats at different points in the season. And what they've also found, so it's true that if you fix the time, you should see this 1,000 minus W, but they've also found that it varies with the season, but of course repeats every year. So it's also proportional to 1 plus the cosine of pi t over 6. So that this is how often does this repeat? Well, every time cosine goes around every time the angle goes around 2 pi, cosine repeats. For this to be 2 pi, t would be 12 months, right? So this repeats every 12 months, right? So what this says is when t is 0, so that cosine is 1, this is bigger. So in January, yes, because it's so cold, the rate of change of the number of coats they've sold is big. When t is 6 months, so you'd be in July, the rate of change in coats sold would be 0. In 6 months, this part would be 0, but then you'd get a 1. So, what am I saying? When t is 6 months, so you're in July, this would be the cosine of pi, that's minus 1. So plus 1, you'd get 0. So it's saying there's no rate of change in coat sales in July because it's a heavy wool coat and it's July. Okay, so this is the differential equation that we get. They also see what happens at the very beginning, and they estimate that the rate of change of coat sales at time 0 is, and I want to match what's in the book, it's 20 coats per month. So we have 2 pieces of initial data. This is good because we'll get some constant that we don't know when we solve the differential equation, but we also have this proportionality constant, which we don't know. So the rate of change of coat sales, it's proportional to the product of 2 things. The number of possible buyers that still haven't bought one, that's the 1,000 minus W, and this seasonal factor that's kind of it's there because there's more demand when it's colder out. Okay, so we'd like to solve this. And well, this equation is separable. Divide both sides by 1,000 minus w, multiply by dt. But before we do that, it's kind of cool here. You can immediately solve for k without solving the differential equation. This happens sometimes. It doesn't happen too often, but at time 0, we're given both the rate of change and the value of w. Well, then we can plug that in and solve for k. This differential equation holds at time 0, so dw dt is 20. So at time 0, you get 20 has to equal k times 1 plus, when t is 0, cosine of 0 is 1, so this is 1 plus 1, and w is 0 at time 0, so we get 1,000. So what do we get? We get that k is 20 divided by 2,000. That's the same as divide numerator and denominator by 20. 1 over 100. 0.01. 100th. That's k. So we've got the differential. So now we've got initial condition that w at 0 is 0. And we've got the differential equation dw dt equals 0.01 times 1 plus the cosine of pi t over 6 times 1,000 minus w. This is separable. You divide both sides by 1,000 minus w. You multiply both sides by dt, and you integrate. So we do that. We get the integral of 1 over 1,000 minus w dw equals the integral of 0.01 times 1 plus the cosine of pi t over 6 dt. This. All right? We've integrated something like this several times now. You let u be 1,000, well, except we didn't have the minus sign. But we could factor that out. So you can pull out a minus sign and then have plus w and minus 1,000. Now this is like something we've done several times recently. You make the substitution u equals w minus 1,000, so that du is dw, and this side just becomes negative the natural log of the absolute value of w minus 1,000. You actually make the substitution, but it's simple this time. It's just not true that the integral of 1 over anything dw is the natural log of the anything. This is just so close to being w. It's w minus a constant that it works out in a very simple fashion. And then we have to do this part. Pull out the 0.01. It's a constant. We get 0.01 times. Well, then you split up the sum. The integral of 1 with respect to t is just t. But then we still have plus. So we still have plus the integral of cosine of pi t over 6 dt. All right. So we need this integral. You do a substitution for that. Let me do it off to the side. So we need the integral of cosine of pi t over 6 dt. You make the substitution. You let u be pi t over 6. Right? You look at that and you see it's one function done to another function, and the inside function is just your variable times a constant. Then this substitution will always work in that case, if it would be something you knew if you didn't have that constant there. And so du is just pi over 6, so it's the derivative of this times dt. It's pi over 6 times dt, which means dt is 6 over pi times du. And so this integral becomes the integral of, this is cosine of u. The dt is pi over 6 times du. Pi over 6 is a constant. You pull it out. So you get 6 over pi. 6 over pi is a constant. You pull it out. Times the integral of cosine of u du. That's the sine of u plus a constant. And then you put back in that u is pi t over 6. So we get 6 over pi times the sine of pi t over 6 plus a constant. So that's what we get. And that's what goes right there. So we get negative the natural log, the absolute value of w minus 1,000 equals 0.01 times t plus what we just found, which is 6 over pi sine of pi t over 6. And then we could have a plus c that's also multiplied times the 0.01, but then that would just be another arbitrary constant for us. So I'll just put a big plus c over here. All right. That's what you get. It's not so attractive, but it's not so bad. We'd like to solve for w explicitly, which we can do. You negate both sides, so move this minus sign over there. So negative 0.01. Then we'll raise e to both sides, remove the absolute value signs, factor off the e to the c, things that we've done a bunch of times now. So you raise e to both sides, and you get the absolute value of w minus 1,000 equals, I'll split off the e to the c. You get an e to the c times e to the negative 0.01 times t plus 6 over pi times the sine of pi t over 6. All that's in the exponent of the e. So let me make sure I copy that right. T plus 6. Yes. Now you take away the absolute value signs. That means you have to put a plus or minus sign over here. As we've done several times, plus or minus e to the c. Just call that some new constant name. You could call it c again, but I usually change it when it's that kind of constant, so I'll just call it b. We get this. Now would be a good time to plug in the initial data. When t is 0, w is 0. So w is 0 when t is 0. When t is 0, we get 0, e to the 0. Right? This is 0, sine of 0 is 0. So all this is just 0. So we get b is negative 1,000. So b is negative 1,000. And if you put that back up here and put that 1,000 on the other side, you get our solution for the number of coats sold. It is minus 1,000 times e to the negative 0.01 times t plus 6 over pi sine of pi t over 6. This is the number of coats sold after t months. So this many coats sold in this small city, sold after t months. I do have the numbers for this for some 6, 9, and 12 months, and they're in the book. It is kind of interesting to see what you get. If you plug in 6 and get out a calculator, you'll get that this is approximately, in the book, they're given to, I don't know, 10 decimal places or so, because in the book we compare this with what you get from linear approximation, but I'm not going to now. So this is approximately 658.24 coats. So, you know, you don't want to sell fractions of a coat, but you know, if you're using this as an estimate, at 6 months you would estimate you would sell 58 coats. At 9 months, you get approximately, this is 68.45 coats. So as an approximation, you could either 68 coats, or you could go, I mean, even though this is below 0.5, 68, 69 coats. And then after a year's gone by, so when t is 12 months, 113.08 coats. So almost exactly 113. Which is somewhat less than double what was sold after 6 months. As you see, in this 3-month period, they sold 10 coats. In the next 3-month period, sold more like 40. In the next 3-month period, yeah, they sold more like 45 coats. 6 months in, if you start in January, is in July. So between July, August, and September, they only sold like 10 coats. Well, yeah, they're heavy winter coats, but in the next 3 months, they sold a lot more coats. Well, of course, it got cold. Okay, the point of this section is, well, that differential equations apply to a wide range of physical problems, word problems, modeling problems. We just saw applications to business, to population problems, to physics problems with objects moving through resisting fluids, and to crime problems where you want to measure, figure out how long a corpse has been dead. Differential equations are one of the most applicable fields of mathematics.